Welcome to World of Rigging, TreeStuff. I'll be your host for the next couple of hours. Before we get into too much depth and discussion, let me go through a quick agenda with you guys, as well as a swift introduction about the company that I work for and myself for the people who are watching but are not familiar with me, my books, or my webinars. Um, for reference, here's a quick outline of our agenda. So as viewers, you guys are kind of aware of what's coming up. We'll look through an introduction, definitions and terms, rigging rope and equipment, mechanical advantage, deflection angles, lifting and lowering, applications, and load balancing. So I hope all those topics sound good to you guys. This slide represents who we are, what we're about. In our line clearance apprenticeship program right now, we have around 230 apprentices between the states of Washington, Oregon, Northern California, and Western Idaho. The Northwest Line, JETC, is a training entity sponsored by the International Brotherhood of Electrical Workers and the National Electrical Contractors Association. We train in the industries of outside power line construction and line clearance tree trimming through registered apprenticeship programs. Since our inception in 1985, we have successfully trained and certified thousands of journeyman linemen and journeyman tree trimmers throughout the Pacific Northwest. We also have a program called Volta. Volta is a pre-apprenticeship course our JATC developed over a decade ago to help people gain an upper hand when first starting out in the line construction industry. With small class sizes, top-of-the-line equipment, and skilled instructors, our graduates do very well in the field. Volta Line is a 10-week course held at our 10-acre training facility and has been engineered to be cost-effective and purposeful for the person just entering the line construction industry. Some training topics include aerial rescue, pole placement, crossarm installment, basic pole and tower structure climbing, distribution circuitry, and AC/DC theory. All the instructors are industry journeymen who bring years of knowledge, experience, and passion to the classroom. All of our instructors are outfitted with Buckingham climbing equipment, and each location has a ton of Buckingham rigging equipment. Chainsaw protection is provided by Clogger. Hoffman Boots is a wonderful company to work with, even helping us develop some new industry footwear that will be coming out soon. Some of you may have seen examples on Facebook that I've shared and discussed. DMM is a huge supporter of our programs, providing their amazing pieces of rigging and climbing equipment to each of our training locations. And of course, TreeStuff and Notch has not only given us the opportunity to provide this webinar to you all, but also help with the logistics and equipment involved to make this happen. So I'd like to take a minute to say thank you to all of our sponsors. So who am I, right? My name is Keith, and I'm an IBW journeyman powerline clearance tree trimmer. I went through a formal education to learn how to trim, care for, and remove trees around power lines. I'm also a proud member of the Northwest ISA chapter, as well as an OSHA outreach instructor and crane examining proctor. So that's a little bit about myself so you guys know my background. As we get into the meat of everything, let's look at a quick disclaimer. Quick and clear disclaimer for anyone and everyone just to make sure no one gets hurt. No act or technique discussed or taught during this presentation is to be done without proper training, licensing, certifications, and supervision. So I hope that's fair with everyone. This is a little tidbit that I learned from my last webinar. People familiar with me know that I use digital examples to recreate real scenarios only because I can't get the perfect picture of everything I want. So some examples are oversimplified to just help convey key points. And I realize many tools and equipment used in tree care have a plethora of appropriate uses left up to the imagination. For the purpose of this presentation, we will be discussing best work practices with a narrow focus on specific uses or applications. This focus will help enlighten some and expand the thoughts of others, each taking away something useful. So let's move on to definitions and examples, just to make sure that we're all talking the same language. These terms are synonymous with with tree rigging and arboricultural work. Most should look familiar to you, but let's take a second to review them, and then we will look at some examples of each. And I'll go ahead and read the examples also. So rigging is both a noun, the equipment used, and a verb, the action of designing and installing the equipment to move a load. Static load. A static load is the weight of the load without any buildup of energy, motionless load without force, pressure, or gravity. Dynamic load. A load can become dynamic when the load is applied with rapid force or pressure to the object. Mechanical advantage. Force amplification achieved by using a tool, mechanical device, or machine to trade off forces, applying them over a greater area requiring less input force. Deflection angles. The angles within a circumference of rigging created by the builder that can reduce or apply the applied weight on the system. And application. The application of putting something into operation, taking the experience of the user, the situation, and given equipment to develop and apply a rigging system properly. Let's move on to some examples and the equipment involved. So on this slide, we're looking at rigging pulleys versus blocks. While I'm aware that DMM Pinto pulleys can be suitable for light rigging, I just want to use this slide to differentiate between sizes and classes, so to speak, to show the differences in size and application. A rigging block, large diameter, cast steel or milled aluminum rope device, appropriate for dynamic and static load lifting or lowering with suitable surface area to attach rope in order to anchor to the tree. And a pulley is small in size and lightweight milled aluminum or pressed steel housing with high efficiency bearings designed for climbing systems and suitable for life support with proper attachments. And I have some examples with me. Hopefully you guys can see these. So if we look at a Pinto pulley versus a DMM large impact block, you can tell that the block is much more designed for heavy lifting and lowering activities. Moving on, let's look at some rope. Now there are a ton of different rope manufacturers, brands, grades, and materials out there on the market. The ones shown are some really popular examples from a reputable rope manufacturer local to me, Samson Rope. Stable braids, hollow braids, and 3 strands. Stable braid ropes offer a durable and easy to handle cordage with great knotability. The heat sensitive features paired with high strength to weight ratios and low stretch make this rope a true winner for tree care professionals when rigging. Hollow braids usually have 12 to 24 carrier strands and allow for an array of configurations due to its spliceability and hollow design. The rope construction is a common choice for many slings used in tree care today. 3-strand rope makes great hand lines and tag lines, easy to inspect, coil, and maintain. It is easy to handle and well balanced, providing many uses. It works especially well with rope jack devices like the Mazda continuous mechanical advantage system, which we'll see later on. Here we see an example. This is a dynamic shock loading representation. A classic example of this, where maybe there was too much slack in the system, or the ground worker held too tightly, or had too many wraps on the porta wrap. The load has gained momentum while falling, then it's abruptly arrested. All of that kinetic energy has to go somewhere, so it goes into the system, giving the climbing arborist a ride. Most of us have been there, and it usually isn't that fun. So that was an example of dynamic. On the other end of the scale is static. Let's take a look at that example on the next slide. A crane is really the best example I could think of for a static lift. The crane picks a weight from the ground. The operator knows the weight, and in ideal conditions, there is no shock loading, no abrupt stopping, accelerating, or swinging that could create a dynamic situation. It's just the static weight of the load. Moving on, next is mechanical advantage, and ways for to pick up, moving on next is mechanical advantage and ways for us to pick up or pull the load. Mechanical advantage. During tree care, in most cases when people are using or discussing MA, they are talking about pulling over trees, pulling tops out, pulling equipment out of the mud. We will look at some examples of that, but also some examples of using mechanical advantage to lift and lower as well. Actually, MA will be a big part of this presentation. So the next slide, we will look at Wikipedia's example of mechanical advantage again. Make sure we are all talking about the same thing. Starting on the left, we see a 1-to-1 with a 4-to-1 on the far right. You can see by the calculations of the 100-pound load getting split up relative to the rope part suspending it, and the amount of input force required to lift the load. Number 2 would be an example of a Z-rig, commonly used and quickly created in the tree care field. The 2-to-1 clearly shows the load being split up, resulting in only an input force of 50 pounds needed to lift the 100-pound load. So this is a really great example, even though there's different parts and pieces involved. As you follow along from a 1-to-1 on the far left to a 4-to-1 on the far right, you can see the load getting split up on the separate parts of line. So we're going to give some examples of mechanical advantage for pulling. So on this slide, we see our worker. He's pulling with all of his might, but he's not using any advantage at all. He is only going to apply literally what he can pull. Let's look at a real example of this on the next slide. So here we have our little guy, and he is pulling the tree with just what he's got, right? That's a 1-to-1. So in a real life example, using a dynamometer, here's me. I weigh 200 pounds on a good day. With me just straight pulling on a tree, I can apply 176 pounds of force onto the rope. That's 176 pounds onto the respective tree being pulled. But how often is that enough, or the amount of pull we need, or that we really want to rely on? It's not often. So we want to use mechanical advantage to help us pull, right? So let's look at a Z-rig or a 2-to-1. So in this example, our little worker has built a 2-to-1 mechanical advantage system. The rope is attached to the tree being pulled, then anchored to the stump, both using some auto-locking notch carabiners and their low friction pulleys to reduce friction on the rope. Using a non-scientific calculation, our worker has doubled his pulling strength. But what about in the real world? In the real world, there is friction involved, and our rope may be wet, our feet could be slipping in the mud, and each of those variables, along with others, could affect a person's ability to apply load on the rope. So let's move on further and continue building this system. But first, look at this example with the dynamometer. So here's an example of me using the Z-rig. I have the blue rope tied off on a tree nearby and the load cell anchored on another. I built my mechanical advantage using an INI as a floating anchor and tossed in a couple DMM pintos. Remember, my input force without any mechanical advantage is around 176 pounds. Using a 2-to-1, I have gained almost 120 pounds of pulling force. Now, is that a significant change? For one person pulling on the rope, it absolutely is. And this is a simple system that can be built with most of the tools and components that you guys already have. Let's take it up a notch and we'll look at a 4-way application. We're using some high efficiency DMM RPM pulleys. This is a compact set of 4-ways with a built-in progress capture pressing. This particular set of 4s is very compact and easy to use, and their built-in swivels make rope part tangles a thing of the past. Again, in our examples, we used an INI to tie a VT hitch on the rope attached to the tree. This makes it great later on if we two-block ourselves. We can tie off the red rope and move the system, resetting it for more pull. You'll see an example of that in just a few slides, but first let's look at my application of using a set of 4s to see what kind of pull I get. With a 4-to-1 application in the real world, we're using 2 load cells, one at the tail hold and another attached on the floating VT anchor. The amount of force seen at the tree is 842 pounds of force. That is over a 600-pound increase from my original 176 pounds of input force. Note there is only 610 pounds of force on the tail hold. The cause of this reduction is the 4-ways themselves. Having the load dispersed between multiple strands of rope, the actual felt weight on the tail hold is less than the tree actually experiences. Examples like this are extremely valuable, especially when there is a tree susceptible to barber-chairing or could be dead or rotten. You have to make sure the tree and any anchors are capable of withstanding the force one person could apply by using mechanical advantage. We've seen this in numerous videos on YouTube, or probably even experienced it ourselves. If the tree that we're pulling and we pull it too hard, we could break it, and once it breaks, there's necessarily no controlling it. So you have to make sure that the equipment that you're using and the tree that everything's being attached to or pulled can withstand the forces that you're going to apply to it. So let's see, let's talk about tube blocking. Tube blocking is a very common problem if you're using any type of fiddle blocks or set of four-ways or anything of that nature. Utilizing mechanical advantage and blocks are a super useful tool in tree care, but one of their biggest drawbacks is when they get tube blocked. For those of you that are unfamiliar with that term, tube blocking is when you have pulled all of your available length of rope, literally running the two blocks into one another, restricting you from pulling any more. So some people call that gear locked as well. That's kind of another synonymous term that goes back and forth. Ways that you can manage and prevent from getting gear locked or tube locked, especially in a scenario where you may need more pull, like you're pulling a tree over and you've tube blocked yourself, but that wasn't enough initial pull to get the tree to tip, so you now need to reset the system. By using a floating anchor like the VT shown, you would attach your mechanical advantage system to the VT. When you have or are about to tube block, the red rope would be tied off to the anchor using something like a rescue aid or puller wrap. Tying off the rope allows your progress to be captured and the MA system to be released and reset. And when I say reset, I am talking about expanding the blocks and the VT back up the red rope, effectively giving you another round of pulling. And this process can be repeated as much as necessary to get the job done. Not only does the puller wrap or a rescue aid provide you a way to tie off the red rope and release the mechanical advantage system, it also provides a backup if that prusik or something in the mechanical advance system was to fail. It provides a backup to where you're not going to lose everything and let that tree tip backwards on the stump. Another common tool used in rope care is the Masdam rope jack or similar rope jacks. According to the manufacturer Masdam, they are in fact mechanical advantage, a 10-to-1 mechanical advantage. But keep in mind, the common 3/4 ton are only rated for just that. 3/4 ton, 1,500 pounds. The best thing about rope jacks like the Masdam pictured is that they are continuous, meaning you will never tube block yourself. You can pull and pull until you either run out of rope or you hit the capacity on the device. Some rope puller and rope jack limitations. The rope jack example, again, is the Masdam because it is the most common in tree care. These rope jacks are designed to work best with 1/2-inch 3-strand ropes, not stable braids or other materials. They will either slip or bind. We teach our apprentices and our journeymen to back these systems up. When I say back up, I'm talking either about a progressive capture or midline knot. On the bottom right of this slide, we can see a green section of rope that has been tied off to the anchor stump, and a Blake's hitch has been tied in front of the device. A rope is pulled into the device. The hitch allows the rope to move inwards, but it would prevent it from slacking outwards if the device was to fail. Progress capture. Also on the bottom right of the screen is an alpine butterfly tied into a blue rope. The midline knot serves a similar function as the Blake's hitch in this example. The downfall would be that the midline knot would have to be tied multiple times, progressing it up the slack tail as more rope was gained through cranking the device, inevitably leading to excess slack, which could be bad if the system was to fail. So instead of consistently tying a midline knot, a better option is by using a Blake's hitch or another similar hitch. A question? Sure, I'd love a question.
Hey everybody, Carson here at the TreeStuff HQ. A question popped up in the chat. Jay Bradley asks, what other knots besides the VT do you recommend using for a floating setup like that?
Sure, so a VT is, first of all, is going to be my number one because I think it's quickly tied and you can easily make adjustments to it by either adding another braid or another wrap. So the VT is always going to be my number one. Another option would be like a distal or a climb heist. A climb heist I use a lot, but I use it more in application for spider leg balancers and situations like that, or foot locking. But it's still a good hitch to use. Things like a taut line, I'd probably stay away from, or Blake's hitch, only because they can bind so tight, and you can put so much pressure using mechanical advantage that hitch can really bite into that rope, making it hard to get undone. Sure.
One more question while we're still on mechanical advantage. Stephen Pearson asks, can you touch on why, when you become the load, like in a moving rope system, do you only pull half your weight?
If a person, okay, let me get this straight. So why in a moving rope system, if you become the load, why you're only pulling half your weight? So in a moving rope system, your load is, again, if I weigh 100 pounds, I am spreading my weight across 2 legs of rope. So it's gone back and forth with controversy on whether or not a moving rope system for climbing is actually a mechanical advantage system or not. And it's sticky, but it can be, because your load is you're essentially pulling half your weight in most, if you're hip thrusting or something along those lines. I hope that answered that question okay. It's kind of sticky, but it's the best I got off the top of my head. All right, so let's continue on, and we'll look at examples of mechanical advantage for lifting, because mechanical advantage can be used for lifting as well as lowering, right? So this slide can be hectic for people that have never seen this type of system before. So if there is any questions about this slide or as we move forward, please don't hesitate to chime in, type them on there, and Carson will help me get those questions answered, okay? So lifting with MA, hold on one second. So lifting with MA can be a great tool for the working arborist. I don't know how many times in my career I've needed to lift a section of wood over a fence, or maybe while lowering, it got caught in the crotch of the tree. Whatever the scenario, each working arborist either has or will run into a situation where they need to lift a load. In this first example, we have taken the same DMM RPM 4-ways used earlier to pull a tree and turn them vertical. So from horizontal pulling a tree, we're now standing the mechanical advantage up. The 4s are attached to the base of the tree and attached to a movable anchor point on the host rope. In this example, we're using a Gibbs rope grab. A rope grab device works well in these scenarios because they can be advanced up the rope with a pull hook. So in this example, the green rope that's attached to the log is the host rope, and that's the rope that the Gibbs or rope grab would go onto. And you would take the pull hook, preferably without a pull saw blade on it, and because the Gibbs only moves one way, you're able to push it up the rope with the pull hook. And this provides the user a significant distance of pulling length before tube blocking themselves. In earlier examples, we talked about backing up our system, and we should always do the same for this kind of mechanical advantage system as well. And by using a porter wrap at the base of the tree, any slack in the rope can be securely tied off in case of system failure, or in case a mechanical advantage system becomes tube blocked and you must reset the system. So again, just like in our earlier example, when we were pulling the tree, you still may need more pull than the length of rope in the 4-ways allows you. So you may have to reset the system. So employing a porter wrap or a rescue 8 or something along those lines at the base of the tree, it gives you the option to tie it off and reset your system. On the next example, we see a tree with either an abnormally large lead over a house or an abnormally small house under the lead. I'm not sure which. Either way, for the purpose of learning, we're going to remove this lead in one section. There could be times where the arborist deems it safer to rig a piece like this whole instead of sectioning it out. And we're going to look at utilizing a technique called double whip. Keep in mind, this technique requires adequate space, and the host anchor, the tree itself, has to be strong enough and tall enough to support this rigging system. So on the next slides, you'll see this kind of standing up, and you'll gain some semblance of how much room there needs to be for this to work appropriately. So dissecting the next example, we have a block affixed to the top of the D-limb leader going vertical, and there's another block installed on the limb to be removed. The rigging rope is threaded through the block on the main leader of the tree, then threaded through the block on the lead that's to be removed, and then brought back to the main leader and secured above the first block. So if you think back a couple slides ago, we talked about a Z-rig or a 2-to-1, and essentially that's what this is. Before any cuts are made, you can see that there is something resembling that Z-rig, right? And it's the 2-to-1 mechanical advantage. In this example, we're using DMM impact blocks, but for smaller applications, lighter duty equipment is acceptable, like the DMM Pinto rigs. On the next slide, we can see kind of what that would look like if that limb is to be cut. So the proper cut to make would be a face cut facing upwards, so on top of the limb, preferably an open face notch. An open face notch is not always the best one, but in this scenario it is. But you should, if you're trying this technique, you should definitely be experienced enough to decide whether an open face or traditional or what have you is going to be most appropriate. The back cut would be on the bottom side of the lead. Pulling tension would be applied to the rope before and during cutting slowly. So tension is being applied and you're cutting slowly, and as tension's being applied, that limb is starting to creep up. Once the limb has been stood up and cut free, it can be safely lowered. This technique allows the arborist to remove rather large sections of wood or limbs while still being able to fit them in a relatively tight spot, because instead of lowering a limb horizontally, you're now going to stand it vertically. So it requires a lot less space to put it in, right? Keep in mind that a tagline is always helpful in situations like this to make sure the butt end does not swing out and hit something during operations. On the next slide, we will take a look at utilizing a porter wrap. In this configuration, it will help us better sustain lowering once the lead has been cut, because in all honesty, if you're using the system, it's going to be a pretty large section, so you want to have a porter wrap involved or some type of friction brake. So in this example, we went backwards in time and installed the porter wrap. The porter wrap provides the ground workers the safety of friction and the ability to tie off the load if needed. When there is any possibility of damage or injury, you should always work to mitigate those possibilities. And sometimes it is simple as using a porter wrap to add that extra insurance. So again, you can see the Z-rig before the lead's been cut, and we have a porter wrap installed at the base of the tree. On the next example, we're going to bring mechanical advantage into this rigging scenario, because if that limb is awfully big, one person may not be able to lift it up and stand it up appropriately. So if it's too heavy to be lifted, we can utilize mechanical advantage to lift this lead. We can slowly stand it all the way up using the mechanical advantage. Once the limb is stood up all the way, the rigging line can be secured and tied off in the porter wrap. Then we can release and remove the MA system from the rope and lower the load like normal. So in this situation, you would have, collapsed the four-way blocks on top of themselves, tied off filled up the barrel in the porter wrap, cleated it off, disengaged the progress capture on the mechanical advantage, disengage the Gibbs rope grab, remove all the mechanical advantage from the host rope, and then you're able to lower it down like normal. This next slide is important to me. It's a photo I snapped while facilitating some EHAT training in California. We can see the person, or we can't see the person pretending to be injured in the bucket, but I assure you that there is someone in there. The crew has installed a Buckingham fiddle block set and boom anchor ring. Both of these are manufactured by Buckingham for aerial rescue systems like this. It allows the crew to efficiently lift a person out of the bucket in a safe, controlled manner. If you're practicing aerial rescue techniques like you should be from the bucket, this is definitely something you should include in your rotation. Lifting an injured or incapacitated person who is slumped down in the bucket can be not only very difficult, but also damaging to both the person doing the lifting and the person who's already hurt. So having this kit, it's worth the money. It may not always get used unless you're using it for training, but if an accident was to occur and you have the system available, you're going to save valuable time getting this person out of the bucket, and you're going to reduce the chance of them getting further injured and reduce the chance of injury to yourself. So I know the picture's kind of small, but the very top arrow shows it's a boom anchor ring. So it's a binding strap that gets anchored to the boom. They have them made for round L-type booms and square Terex booms. And then the Buckingham fiddle block set is attached to that ring, and then it's just slacked down, and it's attached to the person who's in the bucket. It's attached to their dorsal, their sternum. So depending upon the type of harness that they're using, you would connect it right into that life support location, and then disconnect their landing from the bucket. You'd raise them out. Ideally, you have two people involved on the ground. So one person's lifting and holding tension while the other person is kind of cradling that person out onto the ground or out into a safe location or what have you. So lifting with mechanical advantage can also help during rescue situations. So that's just kind of the point of that slide. Moving forward, let's look at some examples of mechanical advantage for lowering. So these techniques are gaining popularity because they are super advantageous to the workers involved and the equipment being used. Plus, it can be easily incorporated into rigging situations where the customers require zero impact methods to be used. They can be quite gear intensive, but they're worth the investment. So on this next slide is kind of an evolution of the same rigging. It's the same spar. On the very far left, we can see where the blocks and the slings have been installed in relation to the notch and back cut, and then the picture in the middle is the same spar after the trunk has started to go, and then the third picture on the right is once the load's been absorbed into the system. And again, you can see that mechanical advantage has been built. So by utilizing two blocks instead of one, we're reducing the strain on the equipment and on the anchor point by effectively creating that 2-to-1 system once the chunk of wood has been cut. The middle picture shows the chunk has been cut and is about to be caught on the blocks, and the picture on the far right shows what the system looks like when all the load weight has been applied. This technique is especially helpful if you need to lift the load back up for any particular reason. Like we noted earlier, sometimes you could be lowering a top and it could get caught in the crotch of the tree or caught in another tree, or you need to clear a fence. So again, now you have mechanical advantage to lift that weight. And just as a little note of information, I know these pictures don't show it, but you should never stack the blocks right on top of one another. They should be offset to ensure they don't collide when the chunk meets the spar. So, just have them kind of staggered or offset, so that way when the top chunk comes down, the blocks don't smash into one another, right? And you don't always have to use blocks in these systems. On the next slide, we'll look at using rigging thimbles in their place, because rigging thimbles can be more cost-effective and easier to use, right? So the system shows two rigging thimbles being used, one large and one small in diameter. These are notch rigging thimbles. And the smaller one is spliced into a Prusik loop, which is the red Prusik, and it's spliced. Excuse me. Smaller one is spliced into a Prusik loop, while the larger is bremeled into the sling in a traditional manner. The system can act much like a generic friction saver, having one small ring and one large ring. The Prusik allows you to adjust the length of the system in relation to the diameter of the wood it's being placed around. But for the purpose of this presentation, we are using the thimbles set in place of blocks for negative blocking. So the last side we were using blocks in a negative blocking situation, and this time we're going to use thimbles. So we'll move on to the next slide and see what it actually looks like. In this really shrunken down example, you can see the blue rigging line has been installed through the rigging thimbles on the spar, and through the individual thimble on the section of wood being lowered, it can then be secured on the spar above where the thimbles have been anchored. So let's take a second to follow the blue rope. We see that it's tied on the top of the spar, and then it comes down and is placed through the thimble on the section of wood being lowered, and then it goes up and is ran through the thimble Prusik or the thimble friction saver that's attached to the spar, and that's that mechanical advantage. Utilizing these thimbles and slings is quicker and easier to install versus a sling and block, because you can quickly tie a cow hitch or a timber hitch with them, versus tying that cow hitch or a timber hitch and then installing a block into it. Plus, they're more cost friendly and they have a wider spectrum of application possibilities, and some other benefits to having. So those are some other benefits to having rigging thimbles in your kit. Now that we've looked at a variety of rigging systems, let's take a look at some of the physics involved. Being able to calculate different factors within rigging can really save you down the road. Having equipment and anchors strong enough to support the forces applied can reduce the equipment damage, property damage, and reduce injuries as well. So on this slide, you guys see some confusing vectors with tangent lines, hypotenuses, and cosines. While these equations are accurate and wonderful for the mathematically inclined individuals, we're going to simplify it for the rest of us, because I am not super mathematically inclined. Some of you may be, but I'm going to try and really boil this down to what we need to take away. The following slides will be a crash course in angles of deflection and how they can severely affect the rigging systems you build in the field. So this document and pictures shown on this slide are from a short read called Engineering a Tree Removal. This was created almost 20 years ago by a tree genius named Mark Chisholm, whom I'm sure most of you have heard of. Mark wrote about deflection angles used in rigging and how the forces can either reduce or increase the load on different points. This simple document is a pillar in my understanding of rigging forces, and I highly encourage each of you to read it. It can be found by simply Googling Engineering a Tree Removal, and it'll come up with a PDF that you can download. Moving forward, we're going to jump into a dramatic evolution of these topics that were found in Engineering a Tree Removal. We need to look at some key terms to kind of make sure that we can all, follow along. So rope angles. The rope lays over a block or pulley. The rope angle is the measurement in degrees between the load side of the rope and the non-working side where it could be tied off, installed in a porter wrap, or held by hand, also known as the included rope angle. Angle of deflection. Like measuring the rope angle in degrees, the angle of deflection is the remaining area outside of the rope angle. This angle can significantly impact the felt weight on the equipment and the resultant force. The resultant is a mathematical number found by a simple calculation using the rope and deflection angle measurements. It is the process of calculating the overall weight felt in rigging. I know that this sounds pretty intense, but it's worth it if you hang out here and continue watching, because there's going to be probably pretty valuable and dramatic takeaways where I think everyone's going to at least learn or maybe see something that's eye-opening. So this next slide is the best example that I could give. We have a protractor that's overlaid a pulley. So a block or pulley, right, is essentially a circle. But we are only using half of that circle as depicted on the right. So that is why 180 degrees is such an important value when discussing deflection angles, because we're only using half the circle. When a rope is laid through a block and both parts are side by side, as shown on the right, the deflection angle is 180 degrees. Moving forward, when we're talking about angles of deflection and rope angles, when these angles are combined, they should equal 180 degrees. So if you can remember that they should equal 180 degrees, if you find the rope angle or you find the rope angle or the deflection angle, you'll know what the other one equals, because either way it's got to equal 180 degrees. I hope that makes sense. So let's take another step forward and see what that looks like in actual practice. So not only will we need some way to show the angle, right? The protractor is what we were using in the previous slide. We will also need a multiplication key. The multiplication key in the center is an Excel, and that is something that I can provide to TreeStuff, and I'm sure they can find a way to be able to make it printable on their website. And if you guys can't, Carson, I'm sorry. The key is what allows us to turn the angles measured into tangible working values. So the key on the far right is Chisholm's, the one first proposed in engineering a tree removal. The one in the center has been adapted using the same formula, but it's in increments of 5 degrees. So using a smaller degree gray area, we can more accurately calculate the forces. So let's put the system into play and see how it checks out. So this example is a static load weight example. And remember, we looked at the definition of static earlier. It's the weight of the load ideally without gravity, without dropping it, without abruptly loading it. It's just the load weighs what it is. And in this example on the right, it weighs 50 pounds. And within the example on the right, the rope angle is 180 degrees. So by using the multiplication chart, we find 180 degrees on the chart and see that it equates to a multiplication factor of 2. So if the load is 50 pounds, we need to multiply 50 times 2, which equals 100 pounds. I'm trying to keep this math simple for everybody. I want you guys to be able to not be scared of this system or these calculations. They're very, very valuable, and they can reduce injury and reduce damage to property. So the anchor point highlighted in yellow is actually seen 100 pounds, not the 50-pound static weight of the log. Remember, if the weight is 50 pounds on one side of the rope, at least 50 pounds has to be applied to the other side of the rope to control it. Right? So let's look at another example. So in this slightly more advanced example on the left, we're going to look at this advanced example, right? And then we'll take a break, and hopefully it'll let you guys kind of absorb it a little bit, and we'll look at some, more, a little bit different examples. So on the left, we have a protractor that has been laid over a rigging system. We can see the area inside the 100-pound load, we can see the area inside. The 100-pound load to the non-working end of the rope provides a 45-degree angle. So we see the little box there on the bottom, and the rope goes up and over the pulley, and then it's out at a 45-degree angle. That's the rope angle. Remember, we're always working within a 180-degree constraint. So what is 180 degrees minus 45 degrees? That equals 135 degrees. And that is our angle of deflection. So we can use the key on the right to find 135 degrees and find out what our multiplication factor is, which in this case it's 1.84. So let's calculate it. 100 times 1.84 equals 184 pounds. This is a prime example of how the angles have deflected the forces from the rigging point. So that 100-pound load, we now know equals 184 pounds of force placed on that rigging point. So moving forward, we're going to talk about shock loading and how the angles of deflection involved can significantly impact the weight that's being applied to the system. So stay tuned. We'll take this break, and I'll see you guys in a couple minutes.
Keep your mouth shut and your ears open. You've got to truly humble yourself every day and realize that one bad decision will be your last if it's the wrong one.
Never stop learning.
Learn and study a good arborist as much as possible. Watch them, watch how they work in a tree.
You know, get their 2 cents, especially in business. That's been the biggest challenge for me is finding out that a relative degree of skill will not carry me through, that I needed to be diligent as well about the business side of things.
If you haven't already gone to some sort of trade show, competition, whatever, get out and just shake hands with people. You'd be amazing. You'd be amazed how welcoming everybody is and how much they want to be there to help you. It's pretty inspirational.
Don't just take one person's advice, seek out as much information as you possibly can.
And also realize that it's not a single man sport. This is a team sport. It's a team occupation. And how we interact with each other and how we make each other feel is just as important as how great you can climb and how wonderful you can rig.
You gotta expose yourself to greatness. You don't settle. If you feel like you're gridlocked and you're not learning, move on and go find somewhere where you can learn and grow, So that's probably the best advice I can give. Soak it up like a sponge everywhere you can get it.
Well, there's a lot of different things that go into the estimation of a tree.
A wise man once told me never assess a tree from the road. Always walk up on the tree, take a look around 360 around the tree. You never know what the backside of a tree holds. It might be rotten and decayed, and that can totally change how you're going to go about removing that tree and what kind of equipment's going to be needed to do that.
I bit a tree by breaking it down bit by bit to the smallest parts of the job.
We look at it from an hourly standpoint, how the salesmen that we have bid a job on how long they think the job's going to take, and they break it down like that. And then I get a work order that gives me an idea of how much time we're going to be spending on a property.
My customers like it when I can break it down for them and itemize it to show them where their money is going, rather than just saying, I think that tree's about $1,500. Well, why? Well, here's why. My time, my guy's time, my materials that I'm moving out for you, and you have 4 comm drops and a hotline right next to the tree. That's how I reached that conclusion.
Also, a big part of it is obstacles, in the way of hazards. Are you removing a monster oak tree, overhanging umpteen million, service drops, primaries, pole-to-pole, houses, garages, you know what I'm saying? Those are all big factors. But I think the biggest one is knowing the capabilities of your crew.
Who do you have there? What skill set is there? What is their speed? How well versed are they in being able to develop a complex rigging situation with no guidance?
I usually gauge the neighborhood that I'm bidding in. I gauge how far it is going to be to have the groundsman drag it out. How much equipment am I going to need? Do I need loaders and things like that, or is this something I can do, by hand? How many guys? How long will it take? And of course, then the obvious things: how big is the tree?
It's a large orchestration of many different moving parts.
I always say there are about 300 different variables that go into the estimation of a tree. For me personally, I know the set rate that I want to get per man hour, and then I usually gauge based upon that, time it's going to take and everything else I'm going to need, try to come up with a number like that.
Very first thing up top is my PPE. I keep my helmet in here, a nice clogger buff. Keep my helmet right where I need it at all times. After that, pop open my interior compartment and we'll take a look. First thing on top is my saddle. Keeping my tree motion, has my lanyard on here, bloodstopper pack kit, akimbo, and everything else that I could possibly need for a day in the trees. After that, I have my chainsaw lanyard, my Saka Neoscinder, a pulley saver for when I'm climbing double rope systems, handsaw, 1 cube, 2 throw line cubes, a zigzag with a chicane, and then my climbing line in the big bag. And inside my climbing line, I've got a Sterling SRT line with a zigzag and chicane on that as well. Notch, wedges for when I'm in the tree, extra foot loops for my Saka, my med kit, and because I'm allergic to bees, I carry my EpiPens. In the very front of my notch bag, I've got a collection of hardware, some thimble, Prosix, a notch throw bag, some extra cordage, and a quickie tool for when I'm using my rope runner. This is my notch bag and all the gear I keep.
Hi, I'm Cale Royer, head party animal at TreeStuff.com. I'm here to make sure that everyone knows about our Tree Stuff Party program. Each month, volunteer arborists from different regions host free recreational climbing events powered by TreeStuff.com, giving local arborists a chance to meet, hang out, climb, and try out some cool new gear in the trees. Every Tree Stuff party is 100% free, so there's no reason to not bring your family, friends, co-workers, and acquaintances. Check our Facebook events page to learn about upcoming Tree Stuff parties, and sign up to be notified when there's a new Tree Stuff party in your neck of the woods at treestuff.com/parties. It's all about seeing friends, making new friends, and having fun in the trees. I hope you can make it to a party soon.
Thank you, everybody, for hanging out. So we're going to start back over on the last slide that you guys looked at, because I know a lot of this can be heavy to absorb. So I'm going to go ahead and just reread and re-go over everything on this slide. So we have the protractor, and it's laid over the rigging example. We can see the text box, angle of deflection, we have the block, the load, and the rope angle, right? On the very far right is the multiplication key. We can see that the area inside the 100-pound load to the non-working end provides a rope angle of 45 degrees. And remember, we're always working within a 180 degree constraint. So what is 180 degrees minus 45 degrees? That equals 135 degrees. And that 135 degrees is our angle of deflection. So we can use the key on the right to find 135 degrees and find our multiplication factor, which in this case is 1.84. So let's calculate it. 100 times 1.84 equals 184 pounds. This is a prime example of how the angles have deflected the forces away from the rigging point. So now that we've recovered that, let's move on and see what this looks like while we're lowering down and catching sections of wood. But first we need to look at static versus dynamic. So when rigging wood to catch and lower, we're not talking static load, we're talking dynamic load. When you take a chunk of vertical resting wood and catch it onto a rope secured through a porta wrap or other friction device, you are creating a dynamic event. From our trusty ACRT manuals, we have learned how to properly calculate shock load. The formula is the load times the distance of fall plus 1 load. So for an example, if we had a 125-pound load, falling 3 feet before it's arrested, plus one load, the 125 pounds. That calculation equals 500 pounds. So our 125 pound load just turned into 500 pounds. So this is why it's so important that when you build your rigging system and you choose your anchor appropriately, your system should be built knowing the highest possible nominal load that it could face. Otherwise, ropes break, equipment breaks, the tree breaks, which we've seen countless times on YouTube. So let's move on. In this slide, you see our spar with the block attached. A green rope is the working rope. We can see the red face notch, and the block is secured about 1 foot below the face notch. On the right is a screenshot of a green log weight chart. And we're working with Douglas fir, very, very common tree in the Northwest. So in this example of dynamic event, we have a 3-foot section of Doug fir at 18 inches in diameter. By using the green log weight chart, we can find that fir at this diameter weighs 69 pounds per foot. Using some simple math, we find that 69 pounds per foot times 3 feet equals 207 pounds. So we know that the load or the weight of the log that we're about to cut is 207 pounds. And our rigging block is placed 1 foot below our tipping point. So we can incorporate our shock load calculations of 207 pounds of Doug fir times 1 foot of fall plus 1 weight equals 414 pounds. That means that 1 foot of fall doubled the weight of the load. But we know that the load and the fall distance are not the only things that we need to consider. We need to know the angles involved as well to completely calculate and know the exact weights involved. On this next slide, we have the same dynamic event with 1 foot of fall. We know that it weighs 414 pounds. The angle of deflection, we're going to say for the example, is 180 degrees. So the multiplication factor is times 2. The resultant force of 414 pounds times 2 equals 828 pounds. This means that 207-pound piece of wood just quadrupled in weight. Imagine if the ground person had slack in the rope, or it was rigged with slack, or the block was lower than 1 foot, and the chunk was allowed to fall more than 1 foot before being arrested. It would be even more, and we're going to show that on the next example. So we've been discussing straight up and down coniferous type trees. We're moving ahead, sorry. So after calculating the chunk of wood being caught, we know it weighs 207 pounds. But in this new scenario, the climber has rigged the block 2 feet below the tipping fulcrum, and the ground person has left 1 foot of slack in the rope. So that's 207 pounds times 3 plus 1 weight, 207 pounds, equals 828 pounds of shock load. 828 pounds with the rope at 180 degrees, which means the ground person will have to apply the same in order to control it. The multiplication factor is 2. So now 828 times 2 equals 1,656 pounds of force is put onto the block and a rigging sling on the spar. That's over 7 kilonewtons. What is the working load limit of the pulley and block and sling that you're using? So, sure, a question. Go ahead.
So, question came up in the chat. If you add a double whip to the load, will that decrease the amount of shock that you're seeing in the system?
Yes, it absolutely will. You're still going to get shock load. You're still going to see a nominal shock load, but that shock load value is going to be split over the amount of parts of line working in the system. So if you guys screenshot it or later on you watch this, or you can find the mechanical advantage slide I used on Wikipedia, you can see kind of how it breaks down. 100 pounds broken down on a 1-to-1 is 50 pounds. On a 2-to-1, 33 and a third, etc. I don't know if those numbers are right, just off the top of my head. But yes, if you use a double whip, you're going to be providing a mechanical advantage and reducing the overall weight that the system is going to feel. So I hope that.
Are you reducing the amount of load on the rigging line or on the anchor point or both?
Both. All the above. Good?
Cool.
Okay. So so far we've been looking at straight up and down coniferous or straight up and down conifer type trees, right? But what if we have a broadleaf tree with a wide and spread canopy without central leaders? So let's take a look at some rigging examples that we would use when we don't have a tall central leader. Butt tying or tip tying on widespread canopies, the length of the lead or limb, and create some serious leveraging situations where the rigging point can fail and break. So let's look at some examples. So we have a big canopied deciduous tree, and the arborist on the right notices and points out a very large portion of included bark and explains that there is a chance one of the leaders could break out from the other in a bad windstorm or heavy snow load, right? So that's the narrative that we're working with, okay? On the next slide, we see that a windstorm came and the tree broke in half. So now we've lost one of the kind of the tall central leaders that this tree had. Moving forward, the next day, okay, the story's getting really excited. We have a school bus full of kids underneath what's left of that tree. This is probably a pretty improbable situation, but it's the best thing I could come up with to give you some examples. So, okay, let's see what we're going to do about this on the next slide. Okay, so this is the fishing pole technique. This fishing pole technique is built using some simple pulleys and slings. So each one is strategically placed to direct the forces into the major portions of the tree and reducing stress on the weakest parts. So we see our little catalog of equipment on the left. We got a DMM Pinto, notch carabiner, and some notch slings. And these are some cost-effective components that can be used to build a fishing pole technique. And if we look right below the crown, we see our little red face and notch placed in there. That's where this is going to be cut. So let's move on to the next slide. And this is kind of arrows pointing where all the forces are going to be placed into the column. The forces are being pushed back into the major column of the tree, dispersed along the major area of the trees and downwards. So that fishing pole technique is really dispersing the weight, and it's very it's beneficial, right, when you don't have, or you have a weak connection point. So if there's included bark, it's rotten, it's been struck by lightning, or maybe another arbor was previously cut on it. When you have a non-sound tree with weak components, by adding and dispersing the felt weight and directing them towards the strongest parts of the tree, you can dramatically increase your system stability. So let's cut that top out and see what that looks like. So not only does this system transfer the stress into the stronger components of the tree, but it also changes the deflection and the rope angles. So instead of the deflection angle being greater with one pulley, it has been reduced. This substantially reduces the resultant force on the rope and the subsequent rigging parts. So keep in mind, when a higher rigging point is not available, the fishing pole is a safe option and worth the time it takes to set up. So I hope you guys took something away from that method. Next, we're going to look at load balancing. And I got to be honest, this is not my picture. So whoever used this picture, or whoever's picture this is, I give you credit. Thank you very much for this wonderful picture of load balancing. the next photo, so load balancing is an important skill for the working arborist or line clearance tree trimmer. Whether the piece is to be rigged is too brittle to sustain impact, or you're craning out a tree top and want the load to be as static as possible, spider legs and load balancing have their place in tree care. A simple 10x sling with a large eye make for real quick attachments and adjustments to the host rope using the clem heist hitch. So on the left, we have the spider leg balancer, 3/8 tennic with a 12-inch eye. It's attached using a clem heist onto the host rope, which is red in the center. And on the far right, you can see how they look combined. So the yellow rope on the picture on the far right is the host rope. And then we have the blue spider leg balancer, and it's balancing that section of wood that we're lowering. So we'll move on to the next slide and see how other components can be placed, like utilizing a rigging hub or a central connection device like the ones pictured, give you the advantages of not just an easy place to connect everything, but they also really allow you to rig in the Z-axis for true three-dimensional systems. So on the top, we have the Rock Exotica bolt. In the center, we got the DMM hub, and the bottom, a Rock Exotica Rockstar. And let's take a look at the next slide and really focus on the bolt. So the bolt from Rock Exotica gives the user an endless variety of possibilities, ranging from heavy-duty lifting and lowering to rescue systems and dynamic rigging. And it's all made possible by the removable pin and well-placed rated holes. So that's the Rock Exotica bolt. But let's take a look at it in application. So this is an uncommon yet amazing application of the bolt is for load balancing. So it's not what it was designed to do. But with the pin removed, eye-to-eye pressix can be installed in conjunction with a short section of rope threaded through one set of the available holes. Utilizing the bolt in this configuration allows the person doing the rigging to tie off one end of the piece being removed, then simply pull taut on the other end. The progress capture hitches do the work of adjusting and holding everything tight for you. So I had this system, built this system, and had it approved through Rock Exotica, so the bolt can be used in this application, just so everybody's aware. So in the next slide, there's a stopper knot, right? It's highlighted with a little yellow circle. The stopper knot is tied so the rope doesn't get pulled through the prusix by accident. And pulling to pre-tension the rope during balancing, the prusix will be pulled up into the bolt, allowing them to loosen so you can get the balancing legs tight. So just like a progress capture system on a set of fours or something along those lines, the bolt is what the prusik runs into. It loosens up, allows the rope to pass through. So you just grab a hold of the stopper knot, pull it, really, really tight or as far as you want, and that's what's going to balance your load. So on the next slide, we see the spider leg balancer bolt system. Maybe you guys can come up with a good name for it. So the system is easily applied to both branches and large sections of wood. Using minimal components in small packages allows the worker to pre-tension all the spider legs from one location after they've been tied on. So instead of running around a top or a crown of a tree or a large lead and physically adjusting, pushing your prusik hitch up or your clem heist, you can stay in one spot and pull everything tight. On our next slide, we're going to look at lowering branches. So we're not going to talk necessarily about speed lining, just simply lowering, right? So any components used extensively for lowering or zip lining should be checked for wear often. So steel rings like the ones shown and other crane rigging component can be found for inexpensive prices and are good alternatives to popular rigging hubs like we've already taken a look at. Lowering limbs provides a good control, less chance of property damage, and reduced cleanup because you're getting less breakage. Not to mention being able to take large pieces whole instead of cutting one large limb into many small pieces. Utilizing a lowering system can also reduce wear and tear on your body instead of holding on to a large limb and hand sawing it. That's wear and tear on your shoulders and your rotator cuffs, etc. So by utilizing limb lowering systems, it's going to speed up production and reduce wear and tear on your body. On this next slide, we see these are photos of the sling setup I used. These are 15 slings in various sizes with inexpensive non-locking aluminum carabiners. The slings never leave the carabiners. They're all banded on, and they're connected to a 7/8 Crosby Crane master link. So it's a large welded steel master link, and it's a great, kind of one size does all central connection point for all my rigging slings. So just some ideas for you guys. Moving on, we're going to look at balance lowering, right? So keep in mind that whatever balancer or the rope that you're using as a balancer should be smaller than the host rope. This is a 3/8 piece of 10x, so it's probably going to be smaller than your 1/2 inch or your 9/16 rigging line. And if you don't have spider leg balancers, right? If you don't have manufactured spider leg balancers, you can take a section of rope and tie a bowline in it with a large 12-inch eye and still do the same thing with a clem heist hitch, etc. So balance lowering, when you may have a dead limb or a large lead, balancing can work in place of sectioning out the limb. By using a short section of rope and tying a quick climb heist, you have a spider leg that you can employ in many different situations. So this is just kind of showing you guys an example of that. On the next slide is lowering in the wind. So this slide's a little extreme maybe. We've got the wind from the left blowing to the right, and we've got the Statue of Liberty. And we don't want the limbs to blow into the Statue of Liberty. That Statue of Liberty could represent a house or a pane window or something along those lines. So what can we do, right? What can we do to control these limbs from blowing around in the wind? On the next slide, we see what I call the carabiner trap method, or carabiner trapping. So we have two different examples, right? Both accomplishing the same thing, just in a different way. So on the left, you got an inexpensive aluminum carabiner, and it's been attached to the lowering side of the rope and the side going up, right? Because it's one rope and it's going like this. In the example on the right, the carabiner is attached to the master link and then back to the rope. And either way, it's going to be trapped, right? The limbs are trapped from blowing in the wind. So anyway, those are kind of my rigging examples that I have for you guys, and my mechanical advantage examples. On the next slide, I want you guys to take a quick look at this. It's so all the things you should have when you're rigging, right? So we have our green log weight chart, our log tape, and a protractor, which I don't know any tree guys that carry a protractor, but I do know a lot of tree guys with hands. So on the bottom is just an example of how you can use your hand to find angles. You need your brain, calculator, or your phone, and the multiplication key, which again, there's some Mark Chisholm's Engineering a Tree Removal, and I'll try and make this one available through TreeStuff. So let's take a look at a review, and then we'll answer any questions, okay? So you guys learned about Northwest Line, looked at the difference in pulley and block application, variety of ropes used in rigging, mechanical advantage for lifting, lowering, and pulling, how to identify and calculate angles of deflection and shock load, how mechanical advantage magnifies one person's input force, various mechanical advantage equipment and their different applications, negative blocking, double whip blocking, and load balancing. So I hope you guys enjoyed it. Let's go back to Carson and see if there's any good questions.
Hey guys, Carson here from TreeStuff. This didn't pop up in the chat, but it is something that I know it might help some people, I hope. Keith, can you walk us through your preferred rigging tools? Rigging ropes, rigging blocks, What do you commonly use and swear by on your daily rigging work?
Sure. I would absolutely be happy to answer that question. So I wish I had it all with you so I could show you guys. But as far as rigging blocks go, due to being cost effective and easy to use, ISC spring blocks are definitely one of our go-tos. The small green half-inch ones you can often find for sale on TreeStuff around $100 a piece. 10x slings, tons of 10x slings. So I splice on my own. Most people are nowadays. But 10x slings, ultra slings, IS slings in various lengths for, just unimaginable possibilities, right? You always need a 10x sling for something. I prefer to use auto-locking rated carabiners for everything. I typically use steel carabiners for rigging and aluminum for life support. And then I showed you guys a picture of my sling rigging setup with the Crosby 7/8 Master Link and various other rigging slings. And then the bolt, I only have one of the bolts, but it's come in handy in some instances. Spider leg balancers. I've got several of those in different lengths ranging from 12 to 20 feet, and they've been used a lot as far as lowering leads or craning out tops of trees, crowns. What else? That's really all that I got off the top of my head as far as the rigging components that go with me every day. Is just my ISC blocks, my slings, my endless loop slings, right, with the cheap aluminum carabiners, and then my actual 10x slings that I can make, loopies out of or what have you. And I have several with rigging thimbles spliced into them. And then a mechanical advantage. So always some form of mechanical advantage. Expensive, but probably the best that I've used is the DMM RPM set. So those pulleys, they're expensive, but there's zero friction and they swivel on both ends. So your rope parts getting tangled it doesn't really happen at all. They're very, very compact. They're light and beating the hell out of them, and they certainly hold up. So they're worth the money. They're the best set of fours that I've ever used.
Do you have any thoughts or experience on the GRCS? I know it is a little pricey, but it is kind of a hot product.
So the GRCS, the Good Rigging Control System, is an absolutely by far must-have if you're a company owner or if you're doing any type of consistent big removals. Even if you come up on that one job and you know that you're only going to use that GRCS one time this year, but you really need it, it's worth buying. So if you can have a Milwaukee or some type of impact drill in your truck and that GRCS, it's going to come in handy. Having the ability to lift and lower enormous loads and control them down to the finite position is an absolute tool or is an absolute value and valuable trait that the GRCS has that most other components or tools in our industry don't have. So if you're thinking about getting one and you can afford it, or if you have that one job where you really need it, it's worth its weight.
An interesting question popped up from John Cole. I'll toss it up on the screen, and because it is kind of complicated, and I hope that you can understand this. But he asks, if you're rigging off a lateral branch and you're taking the brush end off of that branch, so you've got a lateral branch and you're essentially cutting it in half, rigging the piece off of the piece that's still left, is it possible to overload the rigging point with the weight of that brush end that was previously supported by that branch?
Sure. I believe that I understand your question. So, yes, it absolutely is. Generally, right, branches taper as they get further away from the trunk, further away. So, ideally, it's going to have less, the portion that you cut off and lowering should weigh less, right? But yes, you absolutely can overload that limb, right? The lead that you're rigging it back to, that you cut it from. A better option would be to maybe have one block or pulley or a carabiner on the part of the limb that's being left there, and then it running back up to the main central leader of the tree, and then down to the ground. Because what you're going to do is you're adding more rope to the system, you're getting better deflection angles, and in case that host lead does fail or that host limb does fail, you still have the central leader to protect you, and hopefully, there's enough distance there where everything doesn't come crashing to the ground. So yes, you can overload it to answer your question, but I hope I gave you another option.
Jason Dudick, going back to the fishing pole technique, also, hey Jason, what's up? Good to see you. But he says that he's assuming you would have to make sure that each pulley in that system actually sees the load. Because his guess, I assume, is that if it's not seeing a load, then it's not actually doing any work. How would you make sure that each pulley in that system of the fishing pole technique is actually useful in that scenario?
Sure, that's a fair question. I'm not saying go out and buy 10 pinto pulleys just for fishing pole techniques. Honestly, each situation is unique to itself, right? You're going to be talking about different lengths, different angles of that tree. If we go back to the example that I used, obviously it's a pretty dramatic arc. Setting it up, probably I would. If I thought back to my experience, I would have to just say experience. Experience is probably going to be your best bet on whether or not your placement of pulleys is really going to, see the load at all. What I can tell you is, putting more in is not going to hurt anything. But start small, start with what you have, and go from there. And gain, grab some experience and see what happens, but start small and start safe. Good questions, you guys. Good questions.
If anybody's got any more questions, throw them in the chat. Now is the time. I want to say a big thank you to Keith for his time and all of the time that he and I spent banging our heads against computers before we started this webinar. So we'll give it 10, 15, 20 more seconds if you've got a question, and then we're gonna let Keith get back to his family.
Yeah, no, I love everybody in this industry, and I love doing these things. I know I went a little fast through all this stuff. I know it's some pretty heavy-duty material and can be hard to absorb, but I assume that this is going to be available later on YouTube or on Facebook, and you guys can reference back to it. And if you guys have questions, there are people that do know how to get a hold of me, and I'm here, and I'm here for you guys. So if there's questions or comments, try and get a hold of me. Let me know.
Somebody did get in right before the line. Jay DeCoster says, do you prefer blocks or rings for redirects?
I use rings almost all the time for redirects. So the rings, they're just quicker to employ. They're lighter. They're just more forgiving too, as far as abuse goes. The rounded edges all the way. Usually my host 10X, right, is smaller in diameter than the actual shiv on the pulley, or excuse me, on the ring itself. So it sits inside that little concave channel. So even if it's kind of not side loaded but rubbing weird on the thimble, it's not rubbing on the 10X. So especially for a redirect, right, there could be some pretty crazy angles in play. I'd almost use a thimble, as a redirect, unless there's going to be some significant load going on it or significant shock loading, or I'm trying to crane something out. I'd be using a thimble in almost all applications. Very good question.
Awesome. Well, thank you, Keith. Thanks for doing this. Thanks for everybody for hanging around, and I'll sign off here from the TreeStuff HQ, and hope everybody has a good night. Thanks, Keith.
Thanks, guys.